We're going to be talking about fault tolerance with Java using something that I've been working on with a couple other individuals called Aeron Clustering. So a little bit about me. My name is Todd Montgomery. I've been doing high-performance messaging, high-performance networking, and high-performance computing for probably the last over 25 years, I guess. And in a various set of markets, within the capital markets, I'm probably best known for being the co-founder and CTO of a company called 29 West, which was acquired by Informatica, that did high-performance messaging from about 2004 to 2009 when we were acquired by Informatica. Previous to that, I actually worked at a couple other messaging powerhouses like Tolerant and TIBCO on various messaging products. So one of the things we'll be talking about today is the idea of guaranteed messaging or queuing and how that kind of relates to some fault tolerance ways of doing things. But even before that, I actually was a researcher that did research into software assurance at NASA. So I was actually a researcher working for West Virginia University, working on NASA projects. And so this actually has a relevance to us because we're going to be talking about some fault tolerance aspects today. In fact, we're going to sort of start out with some basic mechanisms and work and build them up because they actually have a lot to do with the clustering aspect. And once we have an idea what the architecture of this can look like, we'll talk about why Aeron was a good fit for providing this. And finally, we'll sort of wrap around by looking at what the Java interface looks like. Because it is kind of relevant to the whole way that we've developed this using Java and sort of letting some Java principles guide us. So if we break down the title, we have a couple different things to cover here, and we're going to do it this way. What type of fault tolerance are we actually talking about? Because there's many different ways to do it. What is clustering? Why Aeron? And then at the end, we'll take a look at what it looks like in Java, and sort of see what the commonalities are there. So the first thing, fault tolerance. Fault tolerance has about as well defined as these words, okay? It means an awful lot. They cover a lot of ground. So whenever you see any talk that's talking about fault tolerance or it's talking about clustering and things like this, it sort of has to define what that means. And we're going to actually spend a little bit of time doing this because it's actually very central to some of the reasons why we did this. So the first thing is you have a service. It's running on some sort of hardware. Clients connect to it over some sort of communication mechanism, right? The first thing is it's going to fail. You're going to have all kinds of different reasons why it fails. Some will be software, some will be hardware. One way to provide a little bit of fault tolerance is to put it in the cloud. I'm not being facetious. Once you put something into the cloud, you make it easier to launch quicker. You make it easy to virtualize the hardware. That does take away some sort of faults that can occur. If something does happen and being able to migrate it to a different host and bring it up, that actually is a form of fault tolerance. But it's woefully inefficient for a lot of the things we do because we want to actually a lot of times have the ability to have running replicas, okay? The idea that you don't just have one service, but you have many, and you have many that you can go to. The idea of load balancing comes into play, which is also another form of fault tolerance as well. So these are pretty simple, but it does get a little bit more complicated because once you have multiple versions of something running around, how do you work out how clients connect to them? How do they find them? How do they manage, to actually get to the one that they need? Or it doesn't matter? Well, what a lot of this kind of revolves around is the idea that service doesn't live in a vacuum that's totally stateless. We'd like to think it is, but even REST services have some state associated with them, even if you take that stateless part out of the name, right? So if we do that, it's really that state that's there. Now we can just kick the can down the road, right, and say, well, we're just going to store that state somewhere else in a database, or we're going to store it in a cache, or we're going to, just sort of not realize that it's the same problem. We've just kicked it down the road a piece, right? So we've been building systems like this for years, and it's perfectly fine. They work. If something does work, it doesn't really matter why it's been implemented the way it is. If it works and it meets its requirements, it's actually okay. But what we really want to talk about is the fault tolerance of state, because that's the hard part. And this lives on a spectrum. That state that's shared between those actual running services can go all the way from being totally partitioned so that none of them actually have the same state. They have their individual states, and you just shard and partition that state around for the clients, or it can be totally replicated. We're going to look more on that far right end, the replicated end. And because that's the one, it's the harder one in a lot of ways, and it also is one that is the majority of what we need to do a lot of times. So this is kind of the basis of this, and I want to sort of start this by looking at the enterprise way we do this in a lot of systems. And I'm not talking about, microservices. I'm actually talking about, let's step back a moment. Let's think about ESBs. Let's think about, SOA. Let's think about how these things have looked traditionally. And how they've looked traditionally is like this. You have a client. It isn't communicating directly with a service. It's communicating with a queue or a buffer of some sort. And it's using guaranteed messaging semantics or queuing to talk to that service. And if that service is not there at the moment, its information is being either queued or buffered in some way. Now, the first thing is you should realize is that these two things are very different. But for the purpose of this sort of discussion, we're going to assume they're the same thing, because from this angle that we're going to talk about, they operate exactly the same. And that is, if that service restarts, its previous state is gone, right? We don't have anything within the messaging system, whether it be guaranteed messaging or queuing, that allows us to preserve the current state of the system. The only thing we're preserving is messages that are being sent to it. Now, those messages are going to be held around and delivered, and perhaps redelivered, but we don't have anything that's holding state. So any state that we previously had, it's gone when it restarts, right? We don't have anything there. And because that's not his job, traditionally, these systems have an unspoken requirement, which is the job of the consumer of those messages is not to hold state. It's actually to mutate messages for downstream systems. It's just kicking the can down the road, too. It really doesn't want to hold on to any of that state. And if you design systems which hold that state around, you got to make sure that that state is now fault tolerant in some way. That's fine. A lot of these systems end up, setting alongside caching, setting alongside databases, setting alongside all the other technologies. Because they're only solving a very thin piece of the puzzle. They're only solving that problem of what happens to those messages that are sent while I'm down. This leads us to a couple different things to think about. Even with just that bit of information and just that bit of requirement, we have things like, what does it mean with exactly once versus at least once delivery, right? Do we actually have any system which does exactly once? Not without help from the application, we don't. Something that is from a messaging system designer, if you start implementing these systems, you get into something which is called a blocking act spiral. And the reason it's called a blocking act spiral is because you implement acknowledgments into the messaging system by making them block. They don't just complete immediately. And you wait for an act of an act, which then leads you to, at some point, having to realize that you have to wait for an act of an act of an act. And this ends up until someone says, okay, enough with this. We'll just tell the application that, when you acknowledge data, you still may get it again, unless you tell us something about it that allows us to determine if it's been processed or not. This leads into the problem of when these systems are implemented, not the messaging system itself, but the applications, they tend to be non-deterministic on restart. Testing them so that you get all combinations of data on restart is a very tough thing to do. In fact, it's intractable. An infinite stream, it can restart at any infinite position. You can't test that, right? So you have to break it down into what happens if I lose this type of message? What happens if I lose this other type of message? It's really hard to make these systems deterministic so that you can find issues that may happen, especially across restarts. They typically have a lot of contention and coherence associated with them, which makes them slow. And dealing with poison messages and error queues can be a pain, as well as making things non-deterministic. The problem of a poison message is this type of situation. You restart, you get a message. That message causes you to crash. You restart. That message is still there. You pull it out. You try to process it. You crash. You go down. You keep doing this until the messaging system basically says, you try to do this too much, and it puts this message on an error queue, or it gets rid of it. Or the application says, you know, I think I might have processed this before, so I'm going to take it and I'm going to set it off to the side. So poison messages that cause you to go down when your system is designed that if you go down, you get redelivered data can be problematic. But after implementing several systems like this, having worked with users of these systems for a long time, having used them myself in larger projects, and seen a lot of different ways to do this, there's actually a better way, a much better way to think about this. And it revolves around thinking of the data stream that's coming into any system as a contiguous log of data. And we've heard different systems that use logs and the concept of an append-only log. These are all extremely valuable. But one that is even more important than just the log itself is the idea of snapshot and replay of the log. So let's sort of go through, sort of build this up. Let's say you have a sequence of messages, 1, 2, 3, 4, 5, 6, to some message X. And if you think about the system processing this log of messages, it's going to be very, very deterministic, right? It's going to build up some associated state. And if you execute the log from a fresh state with nothing previous, and you execute it 20 times, you will 20 times result in the same state unless there's something outside the log which mutates that state. Randomness, time, unless time is contained in the log. We'll get into that. But you're going to have the same state, which means that you'll have the same state at 2 if you execute 1 and 2 every time. Well, if you take that knowledge and you take a snapshot of your state at any of these points and sort of roll that up, you now have the ability to, in effect, have the same set of state by having the snapshot and then replaying after the snapshot. Let's take that just a little bit differently. What if I were to say that the state was saved at the snapshot, and we don't mind losing the messages from the last snapshot? Do you know of any system that works like this? Excuse me?
Database with a replay.
Right. Yeah. This concept is used in databases all the time. But I'm actually thinking just get rid of the rest of the log. Most of our spacecraft, Cassini, Mars rovers, a lot of them work on what's called a mark and rollback system. So they take periodically snapshots or checkpoints or something within the system. They then save particular pieces of state so that if there is a crash and you have to restart the whole spacecraft or the rover, you start up at a known point, you know what your state is, and from there you can kind of reconstruct the events. So this concept of marking your state and rolling back means that you're not too concerned with the replay. You just want to not have to go, okay, where in the world in the universe am I? In Cassini's case, if the spacecraft crashes and has to restart, it doesn't know where it is, right? How else would it know? Oh, I can look at the stars and triangulate my position. That's great as long as you're not hurtling towards a planet or an asteroid, right? So you want to quickly kind of figure out where you are, find out what your orientation is, see if you need to do anything quickly. That's why you would have something like that. You may not care about the additional things that you've done since that snapshot or that checkpoint, but you're really concerned in having the right information for that mark and having that mark take effect whenever you do something critical. Another point, what happens if you're rotating the spacecraft and you all of a sudden crash and you come back? Do you know that you're rotating? How would you normally think if you look at yourself and figure out if you're doing this? The delta between two different, if you look at the sky or you look at the walls, right, and you see them moving, well, that's not an immediate thing. But you'd like to know what orientation you're in, right? Different things like this. The amount of state that you need is very small, but it's important. The same thing here. Snapshot's just rolling up those events, the critical pieces of those events that have changed state, and then being able to replay what happens after it. So that kind of mechanism of marking the state that you have in some way that's critical, and then being able to replay the messages that have happened after that, or the events that have happened, which gets you into the current state that you want to be in. That concept that alone of a log that is then you can execute deterministically, and you can kind of shrink it by taking snapshots at some point or your latest snapshot and rolling forward from there. It's a pretty powerful concept. In fact, it's not new. It's done all over the place. And we want to sort of look at it in the concept of what a clustered service looks like. So a cluster service is nothing more than what we saw before. It's a whole bunch of real or virtual machines running a service. And if we take that concept of the snapshot and replay and the log, and we were to replicate it across these machines, okay, so that each different entity had its own copy of that log and could process that log, then we have something that's kind of interesting, right? Now we can do this, as long as it's the same log that each is seeing, we can then be in the same state in each of these. And that gets us to the next point, which is the replicated state machine. This is a replicated state machine. The idea that each replicated service is the same event log, sees the same import ordering. In other words, if there's two different events that come in, they get ordered in some deterministic way so that each replica sees the same order, and we replicate it locally. So instead of it being replicated someplace external, it's replicated local to the state machine itself. And checkpoints and snapshots now are not just some random point in the log, they're actually events in the log. Take a snapshot at this point so that all the replicas should have the same snapshot, the same checkpoint. And what this really does is it's rolling up previous log events, right? We're taking all the events that have happened and we're sort of saying, we don't care about the log anymore, we just want the state that we're currently in. And so there comes a question. We have these replicas and they're consuming the log, they're processing the log. When should a service consume or process a log event? And this is surprisingly not an easy answer because let's take, for example, this. One service on the left here has message 1 and 2. The service in the middle has 1, 2, 3, 4, 5, 6. And the one on the right has 1, 2, 3, 4, 5, 6, 7. So there is 7 messages in the log at least. There might even be more. But not all of them have all the messages except for 1 and 2. So is it a good idea to process 1 and 2? Should we wait until we know it's all the messages? Should we allow any of the replicas to consume whatever message they want? So, they can consume, up to 2, up to 6, and up to 7? Well, there is no right answer to this. It depends on what kind of resiliency and fault tolerance you want. But I'll give you sort of an idea how this is done in Aeron clustering. We actually use Raft. So Raft consensus, basically what it's saying is we want to take the majority of replicas and let them process up to where they have their messages. In the example we gave before, the consensus would be 6, because 2 members out of the 3 have 6. Now, the one who has only 1 and 2, he can't process 6, right? It doesn't have 3, 4, 5, or 6, or 7, so it can't process them. But if it did have those, it could process up to 6. And the reasoning here is that you want a minority partition to continue. A minority partition doesn't mean that you have to stop. So if you lose one of these, you still have one with the messages up to 6. So you can continue operation. What this means is you could totally lose it. You don't have to do anything else. You continue on. The concept of RAF is that it has a strong leader, which means that there is one element of the cluster that is elected to be the leader. This is the one who's responsible for ordering input, and also its job is to disseminate consensus, to say what the consensus of the group is. And this is fairly important. Now, the work in this area of how to totally order messages across different sources, and to figure out what is stable and what's not, and to provide that mechanism has been known since around 1975 when a paper was written by Chang and Maximchuk, and they actually put forward something called the Reliable Broadcast Protocol. And this spawned a lot of different work in this area. The original ISIS systems with atomic broadcast, and virtual synchrony built on top of that so that even across errors and failures, you can have a consistent order. These are concepts that have been around a lot. What Raft really did is to make this a much more well understood and well defined way of doing it. So we have basically a system now that's going to talk in some way across consensus to determine consensus, to order, to do all those other pieces. So what is Raft? Raft is an algorithm with formal verification. It has certain properties. The algorithm does. The algorithm, has a certain set of invariants. It has a certain set of assertions that basically, sort of cover its operating range. But this is a fairly, salient point. But Raft is not a protocol, a specification, or a complete system. You can implement Raft. It's fairly useless if you implement just what's there. You have to actually expand on it. And the reason is because it is an algorithm. It is not a complete spec. TCP is a complete specification. You know how to implement it. You can make it interoperate. It has certain characteristics. When something happens, then this has to happen for all cases. That's not Raft. Raft is an algorithm that specifies most of its operation and has a certain set of properties, very good properties. But to implement in the real world, you have to have more than Raft. And for this situation with Aeron Clustering, we added a couple things which are very important. The first is that the leader doesn't just order events, it actually injects time into the system by time stamping each event. So the individual services don't have their own concept of time separate from the log. The log is time. It's everything. And Raft is specified as an RPC-based kind of mechanic. In the real world, this works until you need to actually go somewhat fast. And to somewhat go fast and to scale, asynchronous operation is inherent. So you have to look at what Raft does, what it relies on from an RPC perspective, and mimic that as an asynchronous process as well. And it turns out that if you have the concept of time and it's being used within a system and it's being enforced within a system, then the concept of timers is something you can provide as well. The idea of scheduling a timer that goes off at some point. The leader is the one who's responsible for time stamping events. It's also the one who's watching for timers to expire. So that's a fairly useful thing that most systems end up building themselves if they go down this path. So we have something which looks a little bit different because the consensus between the different elements needs to communicate with one another, but you don't want the client to have to communicate with every single member of the cluster, but there's going to be one member. So it's going to have to reorder, it's going to have to timestamp events, it's going to have to do all this work. Why not let it be also the one who's communicating with the clients? What happens in the case where you don't know the leader? Well, if you go to any of these, they should know who the leader is, and they can tell you where to go, right? So just a simple redirect. So let's say we have a system like this. The concept of snapshots and checkpoints, the concept of a locally replicated log, the idea of using consensus to determine position of consumption or processing, and a state machine at each of those instances that's running over top of that log. What kind of things can you build with this once you have this in place? And this is really the meat of the talk. Well, first off, this is deterministic. The first thing that you gain from this is a very deterministic system. The log is immutable. You can't go back and change the log entry, but you can append to it. And it could be played. You can stop it and look at the state at any particular point. That's kind of nice. It's kind of handy. It's something that a lot of distributed systems don't have the ability to do. And you can also replay. You can go back to a previous state and replay. And since each event is timestamped, you know the concept of how time is progressing. And when services restart, they restart from a snapshot and a log, so they build their state up or read it in the case of a snapshot, and then they adjust it from there. So with that, what can you do? Well, some of the easy things that come about from this is you can do distributed key value stores almost in a simplistic manner, right? They're replicated, so the state in that event stream is just the same event stream. Now this is by far, not maybe the best way to implement them because it does have some additional overhead. You can start relaxing certain things like the order of messages and the concept of time and other things. And you can still do distributed key value stores with, a little less stringency. That will still operate just fine with different types of algorithms. But you can implement a key value store dead simply. The concept of a distributed timer. How many times have you needed the ability for a timer to go off in a system, but you didn't have an element which was, waiting and making sure that it went off? Think about this for a moment. You have an element that comes up and it says, at time 10 o'clock, I want you to send a message to some other entity that doesn't exist right now. But at 10 o'clock, I want, that it will exist there, and I want you to send a message at that point. That's a distributed timer. So you set it up, you let the cluster worry about it, and when the time comes up, the leader expires the timer, causes all the replicas to do whatever they're supposed to do on that timer. And by the same token, now since you have the same state, you can do distributed locks in a fairly easy and cheap way. But so these are sort of the really simple things you can do. But if you start to sort of step back and what are the things that have used these types of systems before? Well, in finance, there's several ones. So there are a large set of matching engines that work this way. They have an immutable log that's called orders coming in. They then match, those who want to sell with those who want to buy. And since it's the same log, it's very deterministic. Now, if you've ever written a matching engine, thinking of it as being a deterministic thing, might be something that is kind of incongruous. It might not be something that you think of. But they can be made to be very deterministic in this regard. The second thing is order management. So you're managing orders from various venues, from different entities that want to buy and sell and do all kinds of interesting things. Tracking that as a series of messages that is coming in efficiently is one thing that you can do. Market surveillance. It's a stream of messages that are coming out, out from a market. If you want to surveil it and watch for certain things, this is one way of doing it. Because now you actually have the ability to say, this event spawned this other event. I now have some correlation. I can even look at the time between them, do all kinds of different things. And from this, you can do, P&L risk, even reference data and different things that might change and might modify. Now you can actually do that on that same stream of data. But, finance is one thing, but, beyond that, what type of systems do we have that would benefit from this? Turns out venue ticketing and reservations is another big system. It's not hard. The logic's not difficult, but the problem is making it so that, if someone decides that they're going to be starting a tour and their tickets are going to go on sale at 6 p.m., you don't want the system to be sitting there and contended on a database by, trying to add tickets to go through all the other process. So managing something like grabbing a reservation while you're checking out and being able to free it later turns out to be extremely easy with these types of systems. Auctions are another one, very deterministic, kind of like matching in some ways. Other ones that are not up here, things like betting and a lot of other systems. Anytime you see a really contended database which has a lot of contention, especially on just certain lines at any one time because of multiple different entities trying to change them, that's a good candidate. These are systems which can be much simpler this way. Now, it doesn't necessarily mean that you need fully clustering. You may not need all of it, but it does simplify things a little bit. And yesterday we actually had a somewhat of a glorified IRC style chat app that went down. Right? It'd be kind of nice if some system like that had the ability to sort of have its that sequence of messages and messages that are coming in be ordered. Right, and also had a little bit more, maybe a little bit more uptime, because our emojis, don't forget about the emojis. Don't underestimate, the importance of emojis. So another system which is kind of built on this idea of an event log or a log of events and is sort of CQRS, Command Query Responsibility Segregation. There's a couple good things and several bad things about CQRS. It's not really related directly to this. It would not be the best idea to use something like CQRS associated with this. And the reason is because CQRS almost demands that you record your outputs. Recording of your outputs can be a very bad thing, especially when your outputs are wrong. So imagine, if you will, you have bad logic that then generates a bad event. Like suppose your logic, your reservation system, your logic says, that it's possible for two people to reserve the same seat. Well, if you recorded that two people reserved the same seat, now you try to replay it, you're kind of stuck, right? So, systems like this, now this isn't a perfect representation of CQRS, and there's lots of little gotchas around it. But, a lot of times, if you're thinking about these types of systems where it's replaying a sequence, in a log, and it's, sort of an event stream, CQRS is kind of built, to do that, but for a different purpose. So, why Aeron? So the first thing is, if you don't know what Aeron is, it's a very efficient, reliable UDP unicast, UDP multicast, and IPC message transport. Think of it as TCP, but over UDP, but it also supports multicast, and it also supports very fast IPC in a couple different languages, in a few different languages. And it's a little bit more than that. It has very fast archival and replay. Now, it's not persistence. It's not guaranteed messaging, because we fundamentally think that guaranteed messaging and queuing are kind of, they're only a small part of a much larger problem, which we talked about, previously. But it does have this very fast way of archiving a stream and replaying a stream. So really what it does is it addresses the efficient bit in the title, right? Aeron has a lot of different pieces that are extremely efficient. So what this really means is, within clustering, if you have Aeron, what it's doing is it's providing all communications. So between different consensus pieces, between services, getting a client sending into the cluster. Aeron publications and subscriptions are used for that. For the storage of the archive, the log archive, it's very simple. Aeron archive and replay is used. And for different pieces of one particular stack, the service, the log archive, and the consensus pieces themselves, we use shared counters and shared memory to sort of control and to monitor one another. And really, the concept of consensus, is built on the stream position. So a stream position in Aeron is a byte within the stream. The stream position 10 is 10 bytes into the stream. We use this for simplifying things like flow control, congestion control, and a whole bunch of other monitoring that comes about by thinking of the, every part of a stream, different components within a stream being in a different position. I'll give you an example. You might be sending and you're at position 100, but an archive might be recording and it's going to be behind that. Well, how far behind it is it? Well, if it's at position 99, it's 1 byte behind, right? If you have a consumer who is only processed up to position 90 and you're at position 100, that there's 10 bytes outstanding. Simple numbers, but the concept here is this. Consensus is nothing more than a number. It's nothing more than a position in the stream that is saying to all the other replicas that you can process up to this point in the stream. This is much simpler than actually a lot of the other things that are done in a lot of wrapped implementations or pieces of them. The other part is batching. Batching is really critical to efficient operation. And how it's efficient is, or sort of critical, is because it has to optimize the pipeline throughput through the system. With clustering, we're not as much concerned about latency. We want lowest latency we can get, but in essence, you also are going through multiple hops. And you're kind of throttled a little bit by how fast consensus can be reached. But one thing you can do is you can stream it very quickly. So you can pipeline that operation. So think of it as the consensus position is going to move just as fast as any of the recordings. So you can go that speed. That turned out to be really quick. How fast? Well, we're still going. But in concept, it can go as fast as your SSD can go. That's it. Or any other storage that you're using. It also turns out that flow control within Aeron, which is one of the few things that, few messaging transports that has flow control, is incredibly important for correct operations so that the system is stable and keeps itself stable. So sort of what does it look like, in Java? Well, the first thing we decided was a lot of the ways that we've seen this done in the past is, this kind of bloated type of, SOE, API, garbage, right? Multiple objects running around that, have 105 methods that you have to fill in if you want to use them. So we decided that A service is a single class instance. It is invoked from a single thread, so you don't have to worry about it coming from different threads or where they're coming from. And it has a very short list of methods. In fact, it has less than a dozen. And they're categorized. When someone connects to the cluster, you get a session open. When they go away, either from timeout or deliberately closing, you get a notification. And this is in the log, so everyone sees them in the same thing. A message is nothing more than, here's a buffer, here's the message, here's the time it was received. You'll notice pretty much everything that is an event has a timestamp associated with it. And when a timer expires, you get notification. How do you take snapshots? System tells you when to take a snapshot. It says, take a snapshot, and it hands you a publication. That's because the snapshot's going to be actually stored in the log archive. So it looks like just sending on a publication, like you were sending data. And if you're loading up a snapshot, it says, here's a snapshot. Read it from this image. And an image is a piece of a stream. And then there's some housekeeping to let you know about certain things. If you're starting up, if you are finished starting up, but you're now replaying, and you've done your snapshot, but you're now replaying, or your replaying is end, or you're ready after you have done your snapshot and replay. And lastly, if your role changes, so that you know if you're the service that is in the leader, or if you're just a follower. And that's it. You just fill in these methods, and that's it. If you don't want to do something, that's perfectly fine. You don't have to fill these in. Now, you can integrate this with some the ways of cleaning up some logic in asynchronous systems, such as RX and Java 9 Flow. It can be done. It's not maybe the easiest or maybe the appropriate thing for certain types of services, but it can be done. What does it look like? How do I get data into a cluster? Pretty simple. First thing is you connect to the cluster, and then you have a buffer that you're going to put your data. You assign it a correlation ID. The only thing about the correlation ID is it has to be increasing. It can have gaps, that's fine. It doesn't have to be contiguous, but it does have to just increase. And you offer into the cluster. Now, one of the things that has normally been done here is that this is a blocking operation. You wait to send into the cluster. And that actually is very important for some systems that need that ability. Most systems do not, though. You'd rather just stream as fast as you can the events that need to go into the cluster. If you need to wait for the cluster to make sure that that message has made it into it, then build that logic into the service. We've noticed several times as we've used systems like this that the thing of I send and then I wait and I block until the cluster has it. Then I send again and I wait until all the cluster has it. What it leads to is this locking behavior that can't go faster. That's basically it's constrained by the speed of light, and it's constrained by every other member of the cluster. It just slows things down. Not everything needs to be that way. You can stream into the cluster and then wait for the end to make sure that everything made it in. So it's a it's a non-blocking type of offer. And receiving from the cluster is nothing more than creating something we call an egress adapter and then polling on it and saying what you want to do with the message. So that's kind of from a high level how things look. So some of the takeaways here. Hopefully I've kind of instilled the idea that snapshot and replay, looks deterministic, can be used if you're not even using something like clustering, but you have the ability to save a recording of events, and you can use those events for mutating your state. Even if you're using something like guaranteed messaging or queuing or anything else of that ilk, you can use that to sort of simplify your state management, especially across a replay. And if there is some power in a timestamp replicated log, right? If you're timestamping it, that means that now the time within your system is decoupled from the real time, and that multiple entities now can rendezvous on the same time without it being something outside of the system, something a little bit more, has a little bit more promise. And the idea of a replicated state machine. One of the things I didn't mention, but should be kind of obvious, is you're reading this log. Everyone's transitioning, based on the same sequence of events. They're kind of not in true lockstep, but they are, sort of progressing at the same pace. So if they process a message, they're at the same pace. And, what do you do for situations like I want to take a piece of data now and mutate downstream? Well, you know when you're the leader, you know when you're not the leader. It'd be easy to have the leader logic to do all the hard work and the rest of it to just sort of sit back and go, well, the leader state machine is going to take care of that. I'm just going to sit here and do the other things that I'd like to do. So you can put conditional logic in and do things like that, or you can just let multiple entities do the right thing downstream. So what's the current status here? Aeron archiving. Aeron's been around since 2014. We've got individuals doing some great things with it, from everything from IoT devices to even some really high volume things in finance. Aeron archiving's been around for probably a little over a year. It's fully supported. It's very fast. We're only bottlenecked by basically storage. And I'm not saying that facetiously. I mean, realistically, we keep getting larger and faster SSDs, and we can't make it, not max them out. Aeron itself, has been known to peg, 40 gigabit, switches easily. So Aeron Clustering, builds on Aeron archiving and Aeron. Currently, it's in pre-alpha. It's actually in production at a couple places. That are using it in a single node version. The multi-node version is coming along and will be in production here in the next month or so, probably even more than that. And I should mention that an entity, adaptive trading, who I don't know if you've ever seen Reactive Trader or anything like that. They are a consulting group who we've worked with for a very long time, and they sponsored this work. They have a client who's actually using this in production, as I said, right now. It's they'll be going into multi-node deployment here very shortly. And just to sort of give you a little bit something hot off the press, last night one individual who was playing with clustering got it running on a set of Raspberry Pis, just to see if they could. And so this is just a simple setup with 3 replicas and 1 client on there. And so that's it. Thank you. We've got about 8 minutes or so for questions, so tried to rush through certain things. Yes?
So with the centralized clock on the master and the timers being shared among the cluster, is there a risk of clock drift or clock asynchronicity biting you during a remastering or failover event?
Not really. So the concept of scheduling a timer is done actually at all of the nodes. The actual expiry of the timer happens on the leader. So if you were to have like a change of leader, a role change to someone else who has a vastly different clock, it would expire, but the rest of them would detect that as well. So because they're all watching that. So think of the entities that are scheduling the timer. All of them are scheduling the timer locally. So think of it this way: none of them have the same time, right? But you're saying I have a deadline of 10 seconds from now, and so it gets scheduled on each of those replicas, 10 seconds from their individual timers. So when, and say the leader is waiting, and he fails, or it fails, right? It goes away. So the leader's now gone. Another leader comes in, and it looks to see what timers it has scheduled. Now it scheduled that timer to go off at 10 seconds from when it scheduled it, right? So within the timestamp in the log, 10 seconds later, it will fire. So there will be 10 seconds, but it's relative to each individual node. And then that gets put into the log, and then it gets replicated, and then that gets the consensus pops up, and the rest of the services then see that. So it's a subtlety, right? Because it's each individual node is scheduling their timer. If they become leader, then they're the one who's responsible for letting everyone else know. So it's always going to be 10 seconds, but it's 10 seconds relative to each individual node.
Can I ask one more follow-up?
Sure. Yeah. No.
If there's drift over a long period of time, say the timer's a month in the future, and the new master's clock has drift, so 1 month wall for it is not the same as 1 month wall for previous master, are there mitigations built in for that? Or ways to protect that?
No, not really, unless you build them into the, but you have that anyway. If you're going to schedule a timer like a month in advance, you're going to have drift within the individual. So if you just had one entity and you had drift, right, you're going to have that drift. So if you wanted to run it so that you had less drift for something that was a long-running timer like a month, you're going to be wanting to do something like PPTP or something else to keep that drift, in check, even if it were just locally to the machine. So it's in effect the same problem that you would have with just one node, because it's still that drift is within that node. It's not between nodes. That's the simplification, right? We're not looking at the skew between two different clocks on two different machines. We're looking at just within one machine. And what it does is it's effectively just adding an event to the log that's saying, as the leader, I'm timestamping the expiry of this event that happens at this time. That's what the new time is. Yeah, it took us. We thought about this a lot. And kind of ran it through several different scenarios to make sure that it's only dependent on the one machine, the leader, at the current time that it expires, because it was scheduled locally to that. Yeah. Sorry. Yes.
I have a kind of related question where the new leader is time-wise behind the old leader. Does that mean that you start getting events that are later offset-wise but have timestamps in the past relative to the previous events? And so the timestamps on the messages start to be kind of out of sequencing if the ordering is still correct.
So the time is a funny thing, right? I'm not being facetious. It actually is a really interesting problem. But realize that when an event happens, it timestamps. The leader timestamping it is assigning the time to it, so that a new leader who comes in is not going to set and roll the clock back to a certain time. He's going to take his time relative to what the old time was. So it moves forward from there. So time always moves forward. Now, you may have a clock on the leader which is unstable, where it drifts around within itself, but you still have that problem however you do time. Time is not always consistent, right? It does vary a bit. It skews within itself. A clock always skews within itself. It'll slow down. It'll speed up based on simply just the physics and the temperature. So the idea of progressing from that time, when you become leader, here's the time, and you progress forward from there, that's a very important aspect of the whole system.
I guess, does that mean that all the second leader is in your system clock on the times that the leaders put in?
We actually do it slightly differently. We don't have the log is the current time in essence. So that's why it comes in every event, and that's why it starts from that. If you become leader, now your job of getting your clock, your system clock, together with the rest of that, and the cached clock, to think of it that way, is now handled from that point forward. What we actually do is within our duty cycle, we have a slow tick that we advance time for. So based on the timestamp of events that come in. So that when we become, if an entity of a cluster member becomes a leader, it then is always going to be ahead of that. It's always going to be basing its basic clock on that plus, however much time progresses, if that makes any sense. Yeah, but all it means is that we're relative, as long as, think of it as, with something like PPTP, you're always having something sending you the time, right? And adjusting your clock. You have the same concept here. You know, it's just that it's actually coming from the leader, giving you the baseline for what the time is. Anything that progresses past that, from a follower perspective, you don't even trust your clock. Your clock is, you know, it doesn't matter. The only clock that matters is the one that's coming in from the leader. When you become a leader, now it becomes important that you know, are at that point and forward. If that makes a little bit more sense. Yeah.
What features a different class say snapshots
Because in Aeron, they're two different things. A publication just sends data, and an image reads data, you know, or pulls data in.
Is it the same thing? Snapshot is a snapshot.
It is. It is.
The right should be the same. Right?
Well, so there's all the mechanics of how you actually are taking the snapshot, right? Internally. If you think about it, all you're doing is you're offering data to a publication, sending data, but it actually is getting stored, you know, in the archive. So we just basically made it as a publication, just that interface. That's the one we had, and we didn't try to make them the same, because reading a snapshot and loading a snapshot, you know, or sorry, taking a snapshot and loading a snapshot, two very different things. We wanted to distinguish them slightly. I'm being told to stop, but I'm more than happy to answer any questions down here. Thank you.